Hello, my name is Mark Georgi and I would like to welcome you to the Catalyst Large Database Analysis Research Workshop. I am going to be teaching you how to access and analyze publicly available medical databases to produce high-quality clinical research. This type of research can be done on your own time, in the shortest time period possible, and on a shoestring budget. I can tell you that large database analysis research has completely transformed my own research career. From an instructor of medicine at Johns Hopkins with no protected time for research, no mentor, and no grant money, I was able to win multiple awards from national societies in my field. This includes the American College of Gastroenterology Auxiliary Research Award for the year 2014, the American College of Gastroenterology Obesity Research Award for the year 2015, multiple oral presentations, presidential plenary sessions, cover articles for multiple journals, editor's choice articles, and even my research being released twice to the mainstream media and me being offered an editorial board position for the journal Gastrointestinal Endoscopy. I look forward to sharing this information with you in the workshop so that with the required resolve and perseverance, you can do the same. I know that because previous workshop participants have already done it. For example, Shaker Eid was one of the first people to take the workshop. Using the nationwide inpatient sample, he won an oral presentation at the American Heart Association Resuscitation Symposium in 2013. He also won an American Heart Association Young Investigator Award in the same meeting and now has more than 15 articles on PubMed using the nationwide inpatient sample. Paul Kroner was another participant in the workshop in 2016. He used the nationwide inpatient sample to win an oral presentation at DDW 2016 the same year. He also won an American Gastroenterological Association Young Investigator Award in the same meeting and an oral presentation at the United European Gastroenterology Week in the same year. Paul has now more than 30 abstracts and oral presentations using the nationwide inpatient sample. During today's online lecture, we will go over the basic statistical concepts you need to know to make the most out of the workshop. We will only cover what you need to know as a clinician without going anywhere near the dreaded mathematical derivations or equations. My goal today really is to make the process as painless as I can. I did include few Stata commands in the lecture today, but these are for your own information only. If you are not familiar with Stata, do not worry. We will dedicate a lot of time in the workshop to make sure you are very comfortable using it. I can tell you this lecture is the driest material in the whole workshop, but on the bright side, it will be over in less than an hour. It is certainly worth the effort. So congratulations for taking the first step towards changing your academic career, and here we go. All right. I will start with the outline as usual. So we will go over 4 basic concepts today: the types of data and how to summarize them, the normal distribution itself, how to check if a distribution is normal, and then the central limit theorem, which is going to be extremely important when we are talking about large database analysis and about large numbers in general. So then again, one of the most important functions of statistics is to transform raw data into a summary that can be easily understood and interpreted by everyone. And I'm going to start with an example. So, which is easier to understand out of these 2 data representations? As you see, this is an experiment we have done and it included 30 participants. The data on the right is displayed in the usual table with participants ranked from number 1 to number 30, and then their age is displayed on the right. Now there is this presentation, but there is also another presentation, which is the one on the left. And then the one on the left comes obviously after applying some statistics. We can see that we have the same information, however the summary of it makes it much easier to understand. The table on the left displays the patient in summary. So we have 30 participants and we have an average age of 34, a maximum and a minimum, and then a standard deviation. Again, we'll cover all of these in details, but just to give you an idea that statistics really has been created to make it easy for people to understand the data we want them to understand. Then again, different types of data are summarized differently, and then therefore we rely on the data distribution to summarize it, and then we're going to go over this in details in the next slides. In general, there are three major types of variables, or as far as large database analysis is concerned, three major types of data we use the most frequently. The first one is the continuous type of data. This is when the value of the variable can be any number, including decimals, from 0 to theoretically infinity. And most of the research we're going to be interpreting and we're going to be involved with includes data that is finite, and an example of that would be age, which can be from 0 to 100, 120, blood pressure, which can go anywhere from undetectable to 220, and can take theoretically any value in between those numbers. There are, for example, total hospitalization charges, which is a common statistics we see in large database analysis research, especially the one using the nationwide inpatient sample. So those are dollars and can go from 0 or free, no charge for the admission, to $50,000, $100,000, $1 million, you name it. So all of these are examples of continuous type of data. The other type is the categorical data. And the categorical data is different from the continuous data, is that here the value of the variable can be one of a limited number of categories. Those categories can be 2, can be 3, 4, 5, 10, 20, but they are finite. And I'm going to give you an example of this. Again, my example is going to be taken from the nationwide inpatient sample, because this is what we're going to be using in the workshop. So for example, if we look at the geographical region that is a variable given in the NIS, we see that the geographical region can be only one of 4 categories, and it could be the Northeast, Midwest, West, and South, so only 4. Another example would be cancer stage. When staging a cancer, we can have a variable that will divide the cancer stage into 3 and only 3 categories. That would be, for example, local cancer, regional invasion of that cancer, and metastasis of the cancer. Yet another example would be a BMI. We all know about the BMI. The BMI can be categorized into 4 categories: undernourished, normal, overweight, and obese. All of them, again, are categories that are finite. They are not continuous. We cannot go from 1.5 to 2.53 here. We only can go between one category to the other. The third type of variable we're going to talk about today is the binomial type of variable. This variable is a special case of categorical variables because it can only take one of 2 categories. So it is either 0 or 1, dead or alive, readmitted or not readmitted, having acute pancreatitis or not having acute pancreatitis. So again, either one of 2 and only 2 categories that this binomial variable can take. These are the 3 major ones that we're going to encounter during most of our research. There are a lot of other types of variables. However, we will not cover those for right now because they are not very common as far as we are concerned. But I will mention a few of them just because you might hear them in the future. And those will be, for example, count data or time to event data that you might encounter when reading journals. But again, we will not cover these during today's lecture. Now we're going to start covering these variables one by one and going over them to understand a little bit more about their distribution and how to summarize them. We're going to start with the continuous variables. Now, in order to summarize continuous variables, we should identify whether the variable has a normal distribution or not. I am sure you have heard about normal distribution, about parametric distribution, and about non-parametric distribution. And today we're going to cover and understand why this distinction is important. Now, just to refresh our minds, the normal distribution is the famous bell-shaped graph, the bell-shaped distribution, where the data is summarized using mean and standard deviation. And I'm sure you are familiar with this distribution where the data follows a curve that is bell-shaped. In the middle of it, there's the mean. To the right and to the left of the mean, we have a data spread that can be divided into units called the standard deviation. I'm sure that in undergrad and in other classes, we were given grades based on this normal distribution. For example, you pass when you're on the 50th percentile, and then you fail if you are 2 standard deviation away from the mean. So the beauty of this normal distribution is that it has characteristics that are very well studied. People have spent decades trying to analyze and predict the normal distribution, and we have a whole lot of information that we can immediately generate once we know that a variable is normally distributed. And this is why it is important that we know whether a continuous variable is normally distributed or not. So now if we do have a normal distribution, we can talk about the mean and the standard deviation. And the mean is the most common measure of location in large database analysis research, because most of the distributions that we will have there are going to be normal distributions. The mean is also called the average, and it is calculated using a formula here that is represented in mathematical equation, but it simply is adding all of the values and then dividing the total number we get by the number of values we added. For example, if we have 5 values, we're going to add the total of these 5 values, and then we're going to divide that total by 5. Now, the standard deviation is also a concept that follows the mean, because it is the indication on how widespread or spread the data is around the mean. And it is the most common measure of spread in large database analysis research. The standard deviation describes the deviation of each value from the mean, or how far individual values are from that mean. And again, the larger the standard deviation is, the more spread individual values are around the mean. And this is how we get an idea of how tight or how widespread the data is around that mean. One concept you might hear a lot also in large database analysis is the variance. And the variance is the standard deviation squared. Again, if you want to look at the mathematical equation, and this is just for your entertainment, I don't expect you to know that. But basically, the standard deviation is calculated by first going through the variance, which is each individual value, xi, minus the mean. So it is xi minus x bar, which is the mean. And then we square that so that we can remove the positive and the negative sign in front of this subtraction. And then we can divide it by n minus 1. Again, this is not important. What it is important to know about the standard deviation is that it measures how spread the data is around the mean. Now, moving on to the non-parametric distribution or the non-normal distribution, those distributions is anything other than the normal distribution. So anything that is not a bell curve, any data that has any distribution other than in a bell-shaped curve, we call a non-parametric distribution. Now, why do we not necessarily like this data? We don't like it because we cannot predict anything out of it. Unlike the normal distribution, where we can have characteristics that immediately can be predicted once a variable is normal, the non-parametric distribution or the non-parametric variables, we cannot predict really anything. This is why we rely on the median and the interquartile range, or the median and the maximum minimum, to describe this data, and we're going to cover that in the next slide. So let's talk a little bit about the median. So the median is the middle number or the 50th percentile in a distribution. And I'm going to give you an example here. Let's take the first line here, 5 numbers. The numbers 7, 3, 6, 9, and 8. Let's suppose that we're doing an experiment and we found that the number of lesions in the lungs in certain individuals are 7 for the first one, 3 for the second one, 6 for the third one, 9 for the fourth one, and 8 for the last one. Now, because we're not assuming that this distribution is normal, what we will do is we're just going to use the mean to summarize this data. And the way we're going to find the mean is we're going to rearrange the numbers that we have had above, and we're going to go from the smallest to the largest, like in line number 2. So now we have 3, 6, 7, 8, and 9. And then we're going to take the middle number. So we're going to count 1, 2, and then from the right, and then 1, 2 from the left, and then the 7, which is in the middle, becomes the median. So the median of this distribution is the number 7. Now, luckily, Stata will do all of this for us, but I just want you to understand how we theoretically can get a median. Then the next immediate question we should have is, well, what if we didn't have 5 numbers? What if we had 6 numbers? And there is no middle number. What do we do? And the answer is, well, we do the same thing. We arrange the data again from the smallest to the largest number. And then we take the average or the mean of the numbers in the middle. And in our example, this is going to be the mean of 6 and 7, which is 6.5. Again, please concentrate on the concept. Stata is going to be there to calculate all the means and the medians we want. We just want to understand how these theoretically are calculated. Now we move to the interquartile range, or the range. This is a little bit trickier to calculate, and basically what we want to do, we want to describe a little bit about the spread of the data. So the range is the distance between the minimum and the maximum. So once we arrange our data from the smallest to the largest, all we need to do is to minus the smallest from the largest number. In our example here, if we have the numbers 7, 3, 6, 9, and 8, what we do is we arrange them from the smallest to the largest. So we get 3, 6, 7, 8, and 9. And then we minus 3 from 9, and then we get 6 as the range. Now this is for the range. What you see usually is not the range presented in papers, but usually you see the interquartile range that is in most papers that you're going to read in the literature. And this value, this interquartile range, is actually also the same concept as the standard deviation. It is a measure of the spread. But the way to do that is to minus the 25th percentile from the 75th percentile, instead of minusing the minimum from the maximum for the range. So again, in our example, we have arranged our numbers from the smallest to the largest. We have 3, 6, 7, 8, and 9 again. The 25th percentile is going to be 6, and the 75th percentile is going to be 8. So what we do is we minus 6 from 8, and then we get 2. So in our example, the interquartile range is 2. Again, concepts are important here because Stata is what's going to help us, and Stata is what's going to calculate all of these values for us. Now the next question that we should ask ourselves is, well, great, now we know how to summarize a normal distribution, and we know how to summarize a non-normal distribution. But then how do we know whether a variable is normally distributed or not? And indeed, there are more than one way to know whether a variable is normally distributed or not. We are going to quickly go over 5 ways to know whether a variable is normally distributed. Those 5 ways are through a histogram, by looking at the relationship between the mean and the median, by looking at the skewness and the kurtosis of a distribution, or by using a statistical test of normality, which we will cover today. So let's start by the histogram. The histogram might be the easiest way to know whether a variable is normally distributed or not. And this is what I usually use in order to quickly determine whether what I'm dealing with is a normal distribution or not. Sometimes it is very obvious, and this is all what you need to do, and sometimes it is not. And then you can go on to look at the other variables and try to decide. I'm sure we all know what a histogram is. The histogram shows the distribution of a continuous variable by breaking the data into bins and showing the frequency in each bin. So here's an example. We have a length of stay in one of the experiments we have done. This length of stay is reported in hours. So we have from 0 to 400 hours here. And we can see that we have a certain distribution that is presented here in a histogram. Now, if we look at this histogram, we immediately know that we are not dealing with a normal distribution. It is easy to tell that this distribution does not follow the normal bell-shaped curve. This is obvious, so you can skip calculations and the other equations that we can do to know whether this distribution is normal or not. What I like about the histogram is, as in our example, it can be a convenient, quick, and intuitive way to decide if a variable has a normal distribution or not. Now, in Stata, if we are looking at a variable or a distribution, we have a simple command to allow us to generate a histogram and look at it on our screen. This Stata command is histogram. You just type histogram, the name of the variable, which I put here as var1, comma, and frequency, to tell Stata that we are looking at a histogram using frequency. Again, here are two other examples to convince you that a histogram sometimes can be the easiest and simplest way to tell whether the distribution we are looking at is normal or not. Let's look at histogram number 1. Is this a normal distribution? I am sure that most of the people who would look at this histogram will recognize that it is very close to a bell-shaped distribution, and therefore the answer is yes. As opposed to the histogram below, most people who look at this histogram will immediately recognize that it does not follow the bell-shaped distribution, and therefore this is not a normal distribution. Now, the second method that we can also use when the histogram does not tell us a lot about the distribution is the relationship between the mean and the median. In a normal distribution, due to the symmetry of the curve, the mean and the median are equal. They are the exact same number. However, in a non-normal distribution, the mean and the median are different. They are different numbers. This is because the distribution is skewed. And I'm going to give you two examples of a skewed distribution. If the median is smaller than the mean, we say that this distribution has a right skew. And this is what we are looking at in the example in front of us. Here in this example, the median of this distribution is 22 and the mean is 28. So we immediately know that this is not a normal distribution. And not only that, because the median is smaller than the mean, this is a right skewed distribution. It has a tail that goes to the right. The opposite of this distribution is the left skewed distribution. This is when the median is larger than the mean. And then we can see that it is a mirror image of what we're seeing in front of us. The tail is going to be on the left. Again, that's another simple way to know whether the distribution is normal or not. Now, the third way is to use the skewness and the kurtosis. And usually we use them hand in hand because both of them are needed in order for us to determine whether the distribution we're looking at is normal or not. And I'm going to give you simple practical definitions of both terms. Skewness is the opposite of symmetry. This means that if the distribution is symmetrical, it is not skewed. The opposite is true. If the distribution is skewed, this means that it is not symmetrical. The kurtosis is the presence of a tapered tail on each end. If you remember the normal distribution, it has two tails, one on each end, and therefore it has a kurtosis. The normal distribution had skewness equals kurtosis equals 0. By definition, the skewness and the kurtosis are 0 to mimic a normal distribution. And therefore, anytime the skewness and the kurtosis are large, either minus 10, 20, 30, 40, or plus 5, 10, 20, 40, 50, we know that the distribution is not normal. The Stata command to look at this skewness and kurtosis is the summarize command. What we need to type is summarize, the name of the variable, comma, and then detail. And here's an example of real-life stata output. This example gives us the length of stay, and I have typed summarize LOS, comma, detail, and I get the numbers below. Those cover a lot of details, including, if you can see, the last two measures on the right lower corner, the skewness and the kurtosis. Here our skewness is 10 and the kurtosis is 265, so we immediately know that the length of stay distribution in our example is not normal and does not follow the normal distribution. Finally, if all above fails, we have a statistical test to tell us whether our distribution is normal or not. We can certainly use their test from the get-go for the people who like to get numerical values instead of looking at graphs, and that's completely fine. And one of the tests used to find out if a distribution is normal is the Shapiro-Wilk score. There are multiple other scores, including the Shapiro-Francia and the Skewness-Kurtosis tests, but we will not cover except for that one test. You can certainly look at the other tests online, or you can come talk to me if you're interested to hear about the other tests, and we can talk about it in the workshop. Again, what's very important to remember about all these tests is that they are a suggestion rather than the truth, since they are all affected by the sample size. If we have small sample size, then getting a p-value of less than 0.05 on these tests is going to be harder, like it is in general. And these tests, all of them, when the p-value is less than 0.05, that is, if we obtain a p-value of less than 0.05, we should consider that the distribution is not normal. The stata command for the Shapiro-Wilk test is the SWILK, the SWILK, and then you can put the name of the variable next to that, and then the stata will give you the test immediately with its p-value. And here's an example, again, the length of stay that we used the last time. We can type SWILK and LOS, which is the length of stay, and the stata is going to give us a table. It has the variable, the number of observation, and multiple other numbers. The most important number for us is the last one, which is the p-value, and this p-value is 0.000, which means that it is less than 0.05, which means that this distribution is not normal, and we already knew that by just looking at the skewness and the kurtosis from the previous example. So all of these tests should give you the same conclusion at the end. Now moving on to the binomial variables. Again, as we said, the binomial variables are a special case of categorical variables because they can only take two values, either 1 or 2, either 0 or 1, either male or female, either dead or alive. And then, therefore, the most common way to summarize a binomial variable is to report it as a proportion. And here's I'm going to give you an example. So if we look at our participants, we can see that they are males and females. So the first participant is a female, and we get a male, male, female, female, male, female, female. And we can just say that, or we can summarize them to make it easier for people to understand the balance between males and females in our experiment. And I think it's easy. We all know how to calculate a proportion. For example, if we want to calculate the proportion of females, we count the number of females and we divide them by the total number of participants. In our example, it's going to be 5/8 or 0.625. Same thing for the proportion of males. We're going to take 3 and divide it by 8 and we get 0.375. If we want to use stata and we have a distribution, I'm going to take a real-life example here from an experiment I have done. So the command you're going to use is the tabulate command. And the way to do that is by writing tabulate and then the name of the variable after it. In this example, I tabulated the female variable. So I wrote tabulate female, and stata gives me immediately the proportion. We get females equals 59.11%. And this is the proportion of females we have in our experiment. Now, last but not least, the categorical variables. And if you remember, the categorical variables are those variables that can only be one out of a finite number of categories. And those are divided into two. One is the nominal and the other one is the ordinal. And again, the difference between the two is small, however it is important. The nominal variables can still take multiple levels, but these levels are not ordered. For example, hair color. We can have blonde, you can have brunette, you can have red, but none of them is higher or lower or smaller or bigger than the other. Therefore, they are equal. Same thing for treatment group. We can have treatment number 1, we can have treatment number 2, and treatment number 3, but no treatment is higher, smaller, or bigger than the other. A third example would be hospital location. In NIS, the location can be rural or can be urban, but again, rural is not higher or smaller or bigger than urban. So therefore, all of these variables are nominal. A table is one of the best way to summarize this type of data because it has no order, and therefore we can just put it in a table and put the proportions under each category. And in Stata, if you have nominal categorical variable, you can use the command tabulate and the name of the variable to get that table that will summarize it. As opposed to the ordinal categorical variables, these are made of multiple levels. However, each level has an order or has a hierarchy compared to the other level. And I'm going to give you an example. If we look at severity of disease, this is very much ordinal because we can have mild, moderate, or severe disease. A mild disease is considered less than a moderate disease, which is considered less than a severe disease. And therefore, this is an ordinal categorical variable. So based on the number of categories, if it is 2, 3, 4, or 500 or 600, we can summarize them as tables if they are few, the categories, or we can classify them as continuous data if they are many, many, many. Because come to think of it, if an ordinal variable has an infinite number of categories, then it becomes a continuous variable. And therefore, we can use either the mean, median, etc., to summarize it. Alright, so now we are going to shift gears and we're going to talk about a very important concept in large database analysis and for experiments that have large numbers of participants anyway. And this is the central limit theorem. Very important. And the concept is as follows. Usually, the mean of the study sample is not the important variable. Usually, when we are trying to estimate a mean, it is not for our sample. It is rather the population mean that we are interested in. So rather we use the study sample to estimate the population mean, which is the important variable. For example, if you are reading a paper and the authors in that paper say that our sample's mortality was 6%, you are going to be interested. However, you are not going to be as interested as in another paper where the authors say that the upper GI bleeding mortality in the United States was 2.2%. So basically, what we would like to do is to go from our sample and infer or guess what the number would be for the whole population. And this is a conundrum. This is the reason statistics was created. It is how to go from the sample and say something about the population that is true. And again, because we can see our sample, we can measure our sample. However, we cannot see the population. We cannot measure the population as a whole. We can easily determine what is the mortality rate in our sample, but it's very hard to determine what is the mortality rate in the United States itself. It's very hard to monitor and measure every single mortality that happens in every single institution in the United States. And this is where the central limit theorem becomes important. And the central limit theorem is the assumption or the principle that allows us to extrapolate what we find in our sample to the population where our samples were drawn from. So, the central limit theorem says that if we look at our sample and if we measure the mean and the standard deviation of our sample, then we can guess what the population mean and standard deviation is as follows. the mean remains the same. So the mean of our sample is the same as the mean of our population. And the standard deviation of our sample allows us to determine what the standard deviation of the population will be simply by dividing the standard deviation of our sample by the square root of the n, or the number of patients we have in that sample. This is another way to put it. If we draw 1,000 samples of 5 from a population with a true mean of m and a true standard deviation of s, so if we take 1,000 different samples of different 5 each time, we take 5 people out of this population 1,000 times, and then we calculate the mean of each of this sample. If we calculate the mean of these 5 people we get, then all of these means that we get from the 1,000 different samples, all of these means, the distribution of these means will be normal, would have a normal distribution, and then the mean of the means of the 1,000 samples will be the same as our population mean, and the standard deviation of the means, so if we take the different means and we calculate their standard deviation, is going to be equal to the sample standard deviation divided by the square root of n. And the beauty of it is that this remains true irrespective of the original population distribution. This could be normal, not normal, skewed, anything, as long as we take a large number of samples from this population, then the mean of the means will be equal to the true mean, and the standard deviation of the means will be equal to s over the square root of n. And this is the central limit theorem. I know this is very difficult to grasp in general or in concept. This is why I'm going to use, and you can use also, this website that has a very nice depiction of what we're talking about. So this is the website here. So this is the original population. For right now, it has a normal distribution, and it has a mean of 16, and we can see here, and the median of 16, the standard deviation of 5, and of course, because it is normally distributed, then the skewness is 0 and the kurtosis is 0. So what we are going to do is we're going to start by taking a sample of 5 each time, and then we're going to take the mean of those 5 numbers. So let's start. Here's the first one. This is our sample. It's 5 values, and then the blue down in the third diagram is the mean of this sample of 5. So here it is. Now let's take another sample of 5, and we get another mean that seems to be very close to the previous one. Now let's take a third sample of 5. Again, the mean is close but not the same. And then another 5. Again, you see how the mean is very close to the others. Another 5. Okay, here what I'm going to do is I'm going to start by taking 5 5s very quickly so that we can get the idea. So here are 3 more samples. Okay, for the sake of time also, now I'm going to go to 10,000, and I'm going to add, 10,000. So each sample is now going to be 10,000 just to expedite things. And here we go. We get all these means together, all these means, another 10,000, another 10,000. I'm going to add 100,000, 100,000. So at the end of the day, we can see that the means down in blue follow a normal distribution. And the beauty of it is that the mean of these means is the same as the mean of the whole population, and it's equal to 16. If you can look here, the population mean is 16, the means of the means is 16. And the same thing can go for the standard deviation. If you look at the standard deviation here, let's put it there. We do it again. All right, let's go 10,000 this time. Okay, here's the standard deviation, another 10,000, 10,000, 10,000, 10,000. All right, so now we have the mean, which is the same, 16, 16, and then the standard deviation is 1.53. If you look at the standard deviation here, we can find 5. And again, if we take 5 divided by the square root of n, we're gonna get the standard deviation here, which is 1.53. And that's the beauty about the central limit theorem. Just by using our samples, we can say a lot about the population mean and standard deviation. And what's excellent about it is it also gives us a way to calculate the mean and the standard deviation of that population. We simply call it mean and we call it standard error instead of standard deviation. When we're talking about the mean of the means, we call it the standard error. All right. Now, going forward, why is the central limit theorem important? Why do we like to have a normally distributed mean of means and standard deviation? Again, because we can tell a lot of things and we can predict a lot of things when we have a normal distribution. And if we examine the normal distribution again, we can already tell that 68% of the population in this distribution lie within one standard deviation of the mean. 95% of this population lie within 2 standard deviations from the mean, and 99% of this population lie within 3 standard deviations of the mean. So any distribution that is normally distributed, we know that if we want 68% of the population, well, 68.27%, then we just go 1 standard deviation from the mean. If we want 95%, well, 95.45%, we go 2 standard deviation from the mean. And if we want 99% of this population, we go 3 standard deviation from the mean. And this is important because the confidence intervals, I'm sure you heard a lot about confidence intervals. These confidence intervals are built around the mean or the value we would like to present by using exactly the qualities and the prediction that we can do using the normal distribution. So, since the distribution of the mean of a population is always normal, the mean of the means, except when it is less than 50, we can always expect that 95% of all possible values of the mean will be contained within 2 standard errors, or the standard deviation of the means is called the 2 standard errors, which gives us the 95% confidence interval. This is how we derive the 95% interval. Again, I said 50 here because below the number of 50, this central limit theorem does not hold true anymore. So we need 50 at least in our sample before the central limit theorem kicks in. So if we have more than 50 participants in our sample, then we can apply the central limit theorem and we can determine what the 95% confidence interval will be as soon as we get the mean and the standard deviation. Now, the confidence interval itself is a set of values that we believe are plausible estimates of the population summary statistics, for example, the mean, whatever we are measuring, based on the sample we have drawn. So, for example, if we have a sample of 1,000 patients, we get their mean blood pressure, it is 120 over 80. Then we can construct a confidence interval around this data, and we can say, well, we know that in our sample the mean was 120 over 80, but then we can extrapolate for the whole population in the United States, and we can say that the mean blood pressure in the United States is going to be 120 over 80 plus or minus 2 standard deviation from the mean, which gives us the 95% confidence interval. These are the plausible values for the mean blood pressure in the United States. And that's very important because now we are talking about the population instead of just talking about our sample. Now it is the industry standard that we present means or any numbers we like with its 95% confidence interval. We don't present the standard deviation or the standard error. We just present 95% confidence interval. And it is an industry standard that is 95. We can certainly present 99%, 92%, 95%. But then, because we know already that 95% we can easily calculate by just going 2 standard deviation from the mean, this is the industry standard. Now, how about 99% confidence interval? We can certainly do that. And because we know that in the normal distribution, if we go 3 standard deviation from the mean, we're gonna get 99% of the population. So then if we would like to present 99% confidence intervals for some reason, then we delete the 2 standard deviation and add 3 standard deviation above and below that mean. And here we go, we have the 99% confidence interval. So, to go back to the confidence interval, central limit theorem, we need to understand and remember that we need 50, the magic number of 50, before the central limit theorem, the confidence interval, and everything kicks in. So then when the original population distribution is normal, the mean and the standard error, or the 95% confidence interval, can be used as summary statistics anytime because the distribution is normal. However, when the original distribution, the population distribution, is not normal, but the sample size is more than 50, well then the central limit theorem kicks in and we can still present the mean and standard error and 95% confidence interval and everything. It is exactly like it was a normal distribution, and that's the beauty of having a central limit theorem and having large numbers like in large database analysis. Now, in the case where we have a distribution that is not normal and we have a sample size less than 50, well then we're out of luck because the central limit theorem does not kick in, 95% confidence intervals do not kick in, and then we just have to go and use non-parametric summary statistics, and those would be the median, the range, the interquartile range, etc. Now, interestingly enough, and as expected, the more sure we would like to be about a confidence interval, the wider that confidence interval is going to be. And therefore, a 95% confidence interval is narrower than the 99% confidence interval, and etc., etc. However, again, the industry standard is 95% confidence interval. When you present that interval, nobody's going to argue with you, and I strongly encourage you to always use the 95% confidence intervals when you're presenting data. All right, now for the last part of our lecture today, I'm just going to be presenting kind of like a rapid fire definitions of terms, because you might read those in the literature, and also because you're going to be using this as summary statistics for your own research. And those, you can just read about them. I just want to present them, and then just going to present a brief overview of how they are calculated, because at the end of the day, Stata is going to be calculating them. We just need to understand what they are. The first one is the incidence. Incidence is the number of new cases in a certain period of time over the total number of patients in the sample in that same amount of time. Therefore, if we have, for example, GI bleeding in the month of June, we have 1,000 people, and then 10 of them died. Therefore, the incidence of mortality is going to be 10 over 1,000, or 1%. So it is the number of new cases, the cases that just happened in that time period, over the total number of patients in the sample in that same amount of time. As opposed to the prevalence. The prevalence, these cases don't have to be new. These just need to be existing. They are the existing cases during that time period over the total number of patients in the sample. So, for example, in the same scenario that we have used before, if we have 1,000 people and then 10 of them developed GI bleeding at the beginning of the study, and then 20 of them developed GI bleeding in the middle of the study, and then another 10 of them developed GI bleeding at the end of the study, well then the prevalence is going to be 10 plus 20 plus 10 equals 40. So it's 40 over 1,000, which is 4%. So these are the prevalence. The difference between prevalence and incidence is that in the prevalence we count everybody that has the disease. They don't have to just had it. They don't have to be diagnosed from it recently. They just had it and we count them. Now you can also hear about the risk of the disease. The risk of disease, or risk, is really the incidence of the disease. It is the same thing. But then when we are talking about disease, instead we can use either incidence or risk. How about mortality rate? Mortality rate are the number of deaths in a certain period of time divided by the total number of patients in the sample in that same period of time. And again, this is the exact same definition of incidence. So the mortality rate is the incidence of mortality, incidence of death. How about fatality rate? Fatality rate, also mortality rate, incidence of death, same thing. Now, we frequently hear about absolute risk difference and relative risk difference, or relative risk reduction and stuff like that. So what is the absolute risk difference? Well, we know what risk is. The risk is the incidence. So then the absolute risk difference between two treatment groups, usually the cases and control, it is the risk of disease in cases minus the risk of disease in controls. Otherwise, it's the incidence of the disease in cases minus the incidence of disease in controls. And these are the new cases that we see in the case, and then the new cases that we see in the control group. That's the absolute risk difference. Now, the relative risk difference, we just take the absolute risk difference and then we divide it by the risk of disease in controls. So therefore, it is the risk of disease in cases minus the risk of disease in controls, and then this number we divide by the risk of disease in controls. And this gives us a scale. It becomes a relative. It becomes a percent, and people like percent. How about risk ratio? The risk ratio is the risk of disease in cases. This time it is not minus, but it is divided by the risk of disease in controls. So then it is the incidence of disease in cases divided by the incidence of disease in controls. New cases of disease in cases over the new cases of disease in controls. And why do we need this risk ratio? Why do we not only use absolute risk difference or relative risk difference? It is because of the contingency tables, the 2x2 tables that we are all familiar with. Once we have a 2x2 tables, it's much easier to report things in risk ratios and odds ratios rather than just risk difference and relative risk difference, although we can certainly choose any of the above and then just present it. There are no rules preventing us from doing anything. However, there are some industry standards or like the way things are done usually in research, and the more you stick with those, the more the reviewers are going to like your papers and going to think you understand what you're doing and going to be more likely to trust you as an author. And finally, we're just going to go over this contingency table, the 2x2 table, and typically the horizontal line is going to be disease and no disease, and the vertical line is going to be exposure and no exposure. And typically we have very specific way we mark or label those cells. We have A when there's disease and exposure. We have B where there's no disease and exposure. We have C where there's disease but no exposure, and D where there's no disease and no exposure. So this is the most common table you've probably seen in journals and in papers. So here's we're gonna go with the odds. So we're gonna go with the concept of odds because this is the number or the statistics that we can use in case control studies. And this can also be the statistics that we can use in any type of study when there's a contingency table. So what are the odds? So for example, let's define odds of exposure in disease group. So the odds of exposure means that we are taking the people who are exposed over the people who are not exposed in the disease group. And that's going to be A over C. So the odds of exposure in a certain group, in disease group, is going to be A over C. And similarly, the odds of exposure in the no disease group is going to be B over D. The people who are exposed over the people who are not exposed. Now, when we talk about odds ratio, which is also the odds of exposure in disease group over the odds of exposure in the no disease group, when we simply just divide the odds of exposure in disease group, like A over C, divided by the odds of exposure in the no disease group, which is B over D. So this when we arrange it mathematically, it gives us AD over BC. This is the odds ratio. This is the odds of exposure in the disease group compared to the odds of exposure in the no disease group. Now, this same odds ratio can also present the odds of disease in exposed group over the odds of disease in the unexposed group. So it is interchangeable due to the mathematical derivation that we are not gonna be going over. So basically, I just want you to understand from all of this that the odds ratio is a numeric or statistics that we can use when we are talking about any contingency table, any 2x2 table, whether this is a case control, a cohort, or everything. And then it is a measure that tells us what is the odds or the chances of being exposed between the disease and no disease group, or also what are the odds or the chances of having the disease in the exposed and non-exposed groups. I know that this is not very intuitive for you, or you're just wondering to yourself why we are talking about this, but during the workshop we're going to talk a lot about it. I just want you to understand the concept and don't worry about the calculations again, because Theta is going to be responsible for all these calculations. All we need to know is just to understand the concept of what an odds ratio is, and we'll let this data do the heavy lifting. And that's it. That is the end of the lecture. Thank you for taking the time to listen. You did great, because I can tell you that the material in this lecture is the driest of all the material I will be presenting in the workshop. But on the bright side, it is out of the way. Now we can hit the ground running at the workshop and learn the interesting stuff. I really look forward to meeting you at the workshop. It is going to be great and exciting. And most importantly, it is going to be very useful for you and your research career like it was for mine. Thank you very much, and see you at the workshop.